All right, good morning, everyone. Thanks again for just being flexible with this. Another change in plans. Hopefully we'll get to a normal week here coming up soon before the semester ends. But anyways, regardless, we're going to make it work. Today we're going to be going on to part 2 of in situ soil stress. So this is our lecture 16. Just to check in with where we're at, a lot on the board here. Just remember, we do have lab 7 that's going to be due this week. That's the permeability, constant head permeability lab. From my announcement yesterday, the lab 8, which is the consolidation one, I just don't think we're going to be able to make that work. So this one is off the board. So we're only turning in 7 group lab reports, but we still have an individual lab report, and that's going to be lab number 9. I will announce that a week early so you guys can get a head start on that, and I will talk in more detail on Thursday, which will be in person. Homework 4 is going to be posted today, shortly after class. It's going to be due a week and a few days next Friday. So yeah, 4/22 at midnight. Exam 2, your grades should be posted by now. I'll return those next lecture. Review those, look at my comments. If there's any questions on how I grade, on what the correct answer is, I'd be more than happy to go over with you. And then just keeping in track with where we are so far. Again, no clay consolidation here. We're going to move a week up, and we're hanging out right here. So we're still on schedule, talking about in situ stress this week. And then we will probably, I don't know if we're going to do problematic soil or we'll talk about delta, the increase in situ stress. So yeah, but finals is coming up soon. April's going to go by quick. So just keep working hard and it'll be over soon. Okay. All right, so we're sticking in situ stress here. Chapter 10 and chapter 6.9. Just briefly what we talked about last week. We were just talking about what the idea of stress comes from, and it's really just thinking of the weight of soil above a certain point. And since this is all transmitted as a body, we look at it in terms of stress instead of force. And this helps us extrapolate it into different cross-sectional areas, different 3D areas, and everything like that. And we introduced the term total stress, which is this gamma times the height of the gamma above that, and that's assuming that this is a homogeneous soil, so all the gamma, all the density is the same. And when we talk about gamma, what we need to think of is the bulk gamma. So we're including the water, we're including the volume of air, we're including everything from that phase diagram. So from the phase, that would be our weight. Well, I guess I have it written here. So from our phase diagram, it will include everything. So if there's water in it, then we need to make sure that we're doing the moist unit weight. If it's dry, then we don't have to worry about that, but we cannot be using like the unit weight of solid or anything like that from our specific gravity. So the reason we care about this is because of the fact that soil fails through what we call a shearing behavior. And this is due to the friction, which is where we actually have these particles, these soil particles, wanting to roll over on top of each other and slide and cause the failing that way. So as we increase the normal force on these soil particles, what we would see is this frictional resistance will also increase, which is good because this means we have a higher strength. So soil increases the strength as the stress increases, but also the resulting load will also increase. And we'll talk about some of the specific cases like that. So as I mentioned before, with total stress, what we're actually thinking of is the phase diagram. So if you remember from our phase diagram, way long time ago, back when it was cold outside, we had solid, we had water, and then we had air. And then we did the mass side and the volume side. You remember we had a total volume and a total mass. So this gamma is going to be mass total divided by the volume total. So we need to account for the type of conditions that we have on our site for this. So if the groundwater table is at the surface here and we have saturated conditions, then we need to include soil and water. But what we see is if, like for example, we have a decrease in groundwater table, right? The groundwater table can change through climate changing or just, different site conditions. We put a pump and we dewater the site or something. If we assume that this stress, this total stress, is the thing that is supporting and it correlated with our strength, if we assume our strength based off of our total stress and we change the groundwater table, then we can easily change the pore water pressure, which means this MT would lose our water, right? So what we end up doing is instead we design for effective stress. Our effective stress is this really high-tech equation here. It is shown by a sigma and then a prime or a sigma apostrophe. I don't really know what that is, but that's what it looks like. And it is equal to the total stress, and then we just subtract out the pore water pressure. And this is one of the most crucial like equations in geotechnical engineering that goes much, much deeper into the theory. Right now, we're just kind of looking into the surface of it. But what it actually physically represents is the intergranular stress. The intergranular stress in granule soils kind of makes sense. It's this connection point where the grains are actually touching each other. And that makes sense because this is where the strength is coming from, right? Like, like these actual connection points is how it is the resistance against shearing. But in fine grained soil, we see that these particles actually aren't touching like they are in coarse grain or sand or gravel or something. So the minerals and the crystals don't physically contact actually most of the times in most sands, but they still did a lot of experimental and empirical research and determined that this relationship for intergranular stress still checks out. So even though physically it makes sense in sands, we still use it for sands and clays when they are 100% saturated. So let's look at a few examples of how to calculate total stress, pore water pressure, and effective stress, because again, like this is baseline for any geotech problem, design problem. First thing you need to do is to determine the stress profiles. So oftentimes we plot them as a profile instead of just one point. And so for this example, it's asking you to do so at points A, B, C, and D, or just drawing the profile of what the stress would look like as a function of depth. So we know that the total stress, again, is shown by a sigma. This is really just equal to the sum of all of the unit weights times their respective heights or thicknesses. So again, the heights would be like this. This would be like H1, H2, H3, something like that, if we had these three layers. And again, this gamma, this would be considered our bulk. So if we're in a dry state, then we use gamma D because there's no water. If we're in a moist state, then we would use gamma M or moist. And if we're in a saturated state, then we would use gamma saturated. So our pore water pressure is shown by a U, and U is equal to the unit weight of water times the height of water. And this is when we have our hydrostatic condition. So the best way to think about this is if the water is not moving, then we just look at whatever point, the height of water above that. That's a bad example because there's no water, but like here, for example, the height of water, if we were at that point, how much water would be above us, then that is going to be that HW. And we know the unit weight of water, at least in these units that we're using, is 9.81 kilonewtons per cubic meter. So effective stress, once we calculate both of those, then effective stress is really easy. It's just the total stress minus the pore water pressure, and then that's it. So what I often think is the easiest way of doing these kinds of problems is to create a table like the one shown below. So we have 4 points that we need, that we care about. So let's just label that A, B, C, and D. And then we know the depth below the groundwater, or sorry, the ground surface elevation is important. This is that ground surface elevation here. GSE, it's often shown as that. So what we'll show here is, well, we know that point A is 0 meters below, point B is 3, and then C is 5, and then we have 9 below that. So let's start at the surface here. So total stress, what is above us at point A? Is there anything above us? Now, if there was loading, or if there was, some type of information, then we would have a stress at A, right? Because there's something shown above us that is loading it. But if we were standing at point A, how much would we have to carry? We would have to carry 0. So our total stress is 0. There's no water above us, so 0. So that means our effective stress is also 0 at this point. So let's just go through the total stress. Actually, we'll do pore water pressure and effective stress here later. But let's see at point B. So at point B, what is above us? We have 3 meters of something that weighs 17.9 kilonewtons per cubic meter. And it always helps to put your units in here. Let me move that over so I have room actually. So again, 3 meters times 17.9 kilonewtons per cubic meter. And that is equal to 53.7 kilonewtons per square meter, right? Because the meter cancels out with one of the meters on the bottom. So at point C, how many layers are above us here? So we have our first layer. So we know that that weight is going to be transferred through, so 57.3 or 53.7. But now we also have 2 meters of something that weighs 17 kilonewtons per cubic meter. And then so for that equals 87.7. So for point D, again, this transfers all the way down. So so what we have is now 87.7, right? Because from point D, the stress right here is 87.7. So we have that 87.7 plus something that is 4 meters, and that weighs 19.5 kilonewtons per cubic meter. And we're at 165.7. So the pore water pressure at point B, how much water is above us? 0. At point C, how much water is above us? 0. At point D, there's 4 feet. So we have 9.81 times 4. We have 39.24 kilonewtons per cubic or per square meter of pore water pressure. So now all we have to do is subtract these two, and that is going to equal our effective stress. So 53.7 minus 0, we have 53.7. 87.7 minus 0, 87.7. And then 165 minus 39.24, 126.5. Boom, we're all professional geotechs now. That's the bulk of it. All right, so let's draw the profiles here, because drawing the profile, what we'll see later on the end of this semester, but also in the kind of part 2 of this class, the tech elective, the design of foundations, drawing the profile, it really helps illustrate the stress distribution and helps with the design considerations of measuring the resulting load on structures or something. So this is what we have the table from before. We know that Let's first draw the total stress here. So this first one will be our total stress. And again, that is a sigma, and it's in kPa. So we know it's 0 at the surface. Now, know it's going to be increasing consistently, but when we change density, what should we see change here? So we're going from a higher density to a lower density. Now, granted, it's not that much, but what would you think the slope would change here? Would it be a steeper or a shallower? Or I guess I did that backwards, but. So a lower value will produce a lower amount of stress. So we should see a less steep curve here, right? So we would see this right here, and it would, so this would be 53.7. This would be 87.7. And then with a 19.5, it should be, it's a little off scale here, but it should be the steepest that curve is, or that line is. Now for pore water pressure, so I should just say pore water pressure, PWP, I often will just use it as that because that's like kind of the technical jargon of it. This is again U. So at 0, or at a depth of 0 at point A, we have nothing. Point B, we have nothing. Point C, we have nothing. But at point D, we do have something, right? We have 39.24, and assuming that the water is staying consistent, so we should have a straight line this whole time. So the effective stress should be identical to the total stress, right? Until we hit the groundwater table. So if we were to just continue to draw it here, this would be what our total stress would look like, but now we are subtracting out the pore water pressure. So we should have a lower value. We have 126.5. And again, these should all be straight lines. We're assuming homogeneous material, so the density is staying the same, through the entire thing, constant density, and then constant density, so the slope stays the same. All right, easy one, right? Let's look at one more to determine the in situ stress. This one looks a little bit more like how an actual design problem would look. One, they would usually always give in elevations. So, construction likes to use elevations instead of depths. So, from the survey and the ground or the subsurface investigation folks, they would, probably give you these layers and elevation just in case something changes, like they have to add an extra layer on top for a fill or remove something or whatever. This one shows a foundation. We don't really have to worry about that. But what we're asked to do is given the soil profile below, what is the in situ effective stress? So only the effective of the soil collected from the Shelby tube. So we see the Shelby tube is collected down here. What we should first see is the groundwater table is here at an elevation of 18. We have saturated conditions underneath it. So the clay and the sand layer makes sense. Above it, we're given the dry density, but we're also given a moisture content. So this right off the bat, if we're given a moisture content, that means we need to determine the moist density. Because remember, we're looking for the bulk. So the dry density and the moist density, if you remember from your first two tests, are found through this relationship here. So we have 15.7 is our dry plus 1.22. And this is equal to 19.15 kilonewtons per cubic meter. You can see that's quite a difference, and that's a huge or really easy to make a mistake here. If we didn't include that pore water pressure in our total stress, and then we could have that issue because this is again the bulk density that we care about. So there's water in the pore space. If we were to zoom in here, we have this little cookie, but there would be also water. It wouldn't be saturated, but there's still a weight of something that's in there that's causing a stress. Okay, so another thing that we would do for this problem is determine the thicknesses just to make sure we don't make any math errors here. So 20 minus 18 is 2 meters. I don't know why this dog is just now starting to bark. I've been in here all day and it hasn't barked until I started recording. So I don't know if you can hear that, but I apologize. And then here we go, 4 meters there too. All right, so we only need the in situ effective stress. So to find that, we first find our total stress, and then we can find our pore water pressure. So again, our total stress is the sum of all these soil layers, and our pore water pressure is just the water. And an important thing to remember with this always is to determine which density, which gamma to use. So do you use gamma dry? Do you use gamma moist? Do we use gamma saturated? So if you're given a moisture content and you're given gamma dry, that means there's some moisture in there and we need to use gamma moist. You need to correct it. If you're told that this is dry soil, then obviously the moisture content would be 0. So you would use dry. And if you're below the groundwater table, then you're assuming you're going to use gamma saturated. All right, so let's look at the total stress first. And then this is from at an elevation of 8 again, so where the Shelby tube is. So what do we have first above that? Well, the whole layer is 4 meters, but really what we only have above this is 2 meters. So let's start from the bottom. So we have 2 meters of something that weighs 21 kilonewtons per cubic meter. And then we also have 8 meters of something that weighs 20.5 kilonewtons per cubic meter. This is our sand. This is our clay. And then we are also going to add, use purple, the dry sand portion. So we have 2 meters of something that weighs 19.15. So again, there's a moisture content here, so we need to use the moist unit weight, not the dry unit weight. All right, so we do all this math out and we see our total stress is equal to 245 kilonewtons per square meter, which is equal to kPa. So I'm just going to start using kPa because it's easier than saying kilonewton per square meter. So 1 kilonewton per square meter is equal to 1 kilopascal kPa. And that's what I'm going to be using from now on. All right, pore water pressure. Pore water pressure. This is just the height of the water above it times the density of water. So at elevation 8 right here, how much water do we have above us? This is equal to 10 meters. So kind of easy math here. So 10 meters, and then the unit weight of water again is 9.81 kilonewtons per cubic meter. So our pore water pressure is 98.1 kPa. Cool. All right, so effective stress now. Whip out the big calculator for this, 98.1, and we have 147 kPa. So this would be the stress at this clay location, at that location where we would collect a sample, and we would need that for determining different lab lab tests and stuff. All right, so those two examples. Let's also recap what we were talking about with groundwater table. So as the groundwater table increases, what we will see is the effective stress. Let me change the color so it doesn't look too crazy. Will decrease. We talked about this from the equation here below. What we're only doing is adding to the pore water pressure. So if we are increasing something that we are subtracting something that's not changing, then our sigma prime, our effective stress will decrease. So if we keep increasing our groundwater table above the ground surface, though, what happens to our effective stress? It stays the same. Because eventually the water, if we increase it above the surface, then we need to account for that in the total stress. We're holding something up at that weight too. So any ponding above the groundwater, like any flooding or anything, that changes the total stress. So that the effective stress doesn't actually change, so it stays the same. Adversely, as the groundwater table decreases, then we would see the effective stress increase. And this again is the intergranular stress, so this could be a good thing, right? Because we know that increases the soil strength. This also, though, increases the pressure on the soil, and we kind of illustrated some of these examples here, where if you were to increase this, then actually this could cause soil decompression. And I'd mentioned this in class. I thought I had this slide, but I at least wanted to share it. Lowering the groundwater table, is this a bad thing then? We especially in agricultural areas need to pump groundwater for surface on, or for use on the surface, like to water the crops and all that stuff. So as we do that, what we learned from our permeability lectures is it actually causes a localized area of withdrawal, or like a cone of depression. And in that area, if we have enough wells pumping out water, then what we could see is a overall decrease in groundwater table. And this could be problematic. And, it's really important for agricultural and stuff, but where soil is highly compressible, such as organics or clays, and when water is in high demand, like droughts or just, arid regions where there's just not a lot of water to begin with, like, or precipitation, I mean, we could have a significant amount of what's called ground subsidence. And if this stays in agricultural areas, then it's not the end of the world. But if this starts occurring in areas with urbanization, and we have houses settling, 20 feet over 20 years, that could cause a lot of damage to infrastructures. And I highlighted one of these examples here on the San Joaquin Valley in California. I want to see if this will actually play. This is an interesting little, a video clip from a news source. It's a little dated now, but USGS is doing a lot of research out here to determine the rate at which the ground is settling. Right now, they've found over 25 feet over the past 50 years. So.
Is facing a different kind of emergency. The state's water crisis is impacting one of the world's most important farming regions, the San Joaquin Valley. The ground is literally sinking by up to 1 foot a year. Then Tracy shows us how the land is becoming as unstable as the water supply.
Every 6 weeks, Michelle Sneed visits this white shed. She checks the pulley system and records a measurement. The numbers show that the ground beneath her feet is sinking.
We're measuring the highest rates we've ever measured here, among the highest rates ever measured in the entire world.
Is a government hydrologist and says parts of California's Central Valley are dropping by 1 foot each year. Some areas are 10 feet lower than they used to be. We would have had many, many feet of dirt above our heads.
He meant soil. I don't know if you caught that.
This is why the ground is collapsing. California's farmers are pumping groundwater as fast as they can in order to keep their crops alive during a drought that has left them high and very dry. But when this much water is pumped out of the aquifer below ground, the clay between the pockets of water collapses and the ground starts to deflate like a leaky air mattress. The sinking is buckling the walls of irrigation canals, damaging pipes, creating giant sinkholes, and cracking homes. This bridge has dropped so much, the water will soon flow over it instead of under it. Fixing the damage could cost more than 100 million tax dollars.
You just have to keep going deeper and deeper.
Steve Arthur is a well driller. Some wells are now 2,500 feet deep. That's 2 Empire State Buildings underground. Water that deep is thousands of years old. But it's desperately needed because more than half of the country's fruits, vegetables, and nuts are grown here.
You tell this farmer he can't drill any more wells. He can't farm as many acres. You're going to go into the store and buy a gallon of milk for $10, a loaf of bread for $5. Then the public's going to say, hey, what happened?
So we see this progression.
All right, I think that's pretty much everything there, but you can watch the full video here and just go on a bunch of California stuff. But really interesting because this shows like, you know, kind of makes sense physically why, you know, you pump something out of the ground, you're losing volume, then obviously you're going to have some type of loss of volume, and that's going to be reflected at the ground surface. But we also now see, like from a geotech perspective, what we're doing, we're changing the stresses, like the intergranular stresses, which is increasing and causing more compression, which obviously will cause settlement. So, you know, like what, again, the whole moral of this whole thing, like us as engineers, what we're doing is we're assigning these math equations and mathematical theories and relationships to physical phenomenon. So this is a really good example of that, you know, property there. Okay, so what we didn't talk about last time, or no, we did talk about this, was upward seepage and also how that affects effective stress. So not only would we have, you know, downward movement of groundwater, but we could also have upwards, and this is really popular in Florida with changing the superficial aquifer and the lower Floridan aquifer, upper Floridan aquifer. So the upward seepage against the groundwater table, so when upward seepage meaning it's against gravity, when we see that this increases, so if we have an increase in flow rate, then our effective stress will decrease. And this is meaning our intergranule connection will eventually go to zero, right? So when this happens, then technically we would have no contact strength. Now this is a certain type of condition called quick conditions or sand boils. Sometimes it's called quicksand, but the technical term is just quick conditions. And this causes what we know as liquefaction. Liquefaction is a term where, I mean, basically that's the technical term for what you probably think of when you think of quicksand. It's a sand that acts like a liquid, so liquefaction. And this happens in earthquakes. This is really common, and it's just due to a high increase of pore water pressure. So this is where the effective stress is equal to zero. This only happens in sand. So if you've ever been actually to, let me see if this video will actually play. If you've ever been to Florida, come on, okay. If you've ever been to Florida, if you've ever been to any of the springs, this one is from Fern Hammock over in Ocala. We have these sand boils where the flow of water, upward seepage in this sand is so high that it matches the sand particles weight, you know, so there's zero effective stress and it essentially looks like the sand is boiling, even though it, it just is not being able to hold up any strength, not even the strength of its own weight of the sand particles. What we see is, again, this is only in sand. So quick conditions are only in sands, and this is because they're highly permeable, right? So if we had clay soil instead, what would happen? right? If we had an upward seepage, we would still see that we would see this increase here. And we would see the effective stress decrease. But again, think about it now. We have these blankets of all these like small little particles where water cannot actually flow through it. So this water cannot actually flow through it. So what it actually does, it cannot change the pore water pressure as easier. So when this effective stress goes to zero, what this means technically is the pressure of the water here matches the total stress. And this total stress can also be known as like the, the self weight. And so if our pore water pressure is greater than stress, then you can probably think of it as like a cork or something. What we would have is what's called heave or blowout. And this is really important because this happens with like little to no warning. If we just like, a cork, like shaking a bottle of champagne, like if the pressure in that bottle reaches a maximum where that cannot hold that cork, then it'll just pop automatically. So this is really important when we're excavating in clays. So let's look at an example illustrating this. So here we have a layer of clay here. It's 20 feet thick. Below we have a sand layer. And this sand layer, what we're going to assume is a aquifer, so water can flow through the entire thing freely. So water can flow through here. So the pore water pressure, or the pressure at point A right here, is illustrated by this tube here. So we have 12 feet of head or 12 feet of pressure here. What we're assuming is this is all saturated. So the groundwater table, so the difference in head is just going to be wherever the excavation is. So what we want to know is how deep can we excavate H until the soil will heave? So what's the deepest we're able to excavate, where here we have this block of soil that has a weight will eventually be less than what the pore water pressure is, and we would have this whole thing dislodge and move out. So this can occur, as we dig, we increase H, so this decreases the total stress from this soil block. But U stays the same in the sand layer. So let's look at point A. What we're looking at is only at point A. So the effective stress, well, again, we heave is when our effective stress is equal to 0. So we do not want it to go to 0. So our total stress would be a function of our depth, which would be this right here. So this would be 20 minus H, right? 20 minus H times the unit weight, which is 120. It's saturated. And then this, I guess this is in feet here, right? So 20 feet minus H, whatever this H is. And then our pore water pressure at A is staying constant. So this is 12 feet times the unit weight of water is 62.4 pounds per cubic foot. So what heave is equal to is when this is equal to 0. So this is the bad condition. So what we would do is we would then solve for H. What we would see is H must be greater than or equal to must be less than or equal to 13.76 feet. So again, this is all from a function of our total weight, or total stress, sorry, times the gamma saturated of our clay. And then assuming that our pore water pressure is staying the same, which is 12 feet times our unit weight of water, and that's because this is our HW here, our height of water above it, or the head, the water head above that. So what this is saying is if we were to excavate down, as soon as we reached a depth of 13.76, then we would potentially have blowout or a heave condition, which is really bad because if there's people working down here in the excavation and then the soil decides to heave forward, then that's not a good condition for that worker. So we'll do a few more examples like this, but heave is really important, and it's only in clay. So quick conditions or quicksand is in sand, permeable stuff, liquefaction. Heave is only in clay. All right, so these are some additional things from, if you want to check them out. I think this guy, even though again this video is kind of old now, he actually makes quicksand and illustrates like the fluidized bed in using air instead of water. So you can actually make a hot tub that is made of fluidized air bed. Really interesting, and goes through the science and makes it fun and stuff. And then also there's this YouTube video too, and I'll post both of these on the Canvas page that you can check out, and they do a good job illustrating how liquefaction works. So thanks for sticking around, and yeah, I'll see you guys in class in person on Thursday. Let me know if none of this is making sense, and I can go into more detail and stuff. All right, guys, thanks. See you Thursday.